I am Deb Marler. I am the owner of Sailing and Boating LLC. I am a U.S. Coast Guard captain. I have been instructing and teaching and being a course creator for people who are sailing and boating. And I have been doing that for the last 6 years. In addition to that, tonight we also have Alex Avalos, who is our guest speaker, who I will introduce here in a moment. And Alex and I have been doing this now. This is our second year. And Alex is a senior meteorologist and manager with WRI. And so I just want to take a minute and really ask you, you know, and just talk a little bit about why we're doing this. And we want to provide you all with the basics so you have a far better understanding of weather reporting, what you're looking at.
Didn't know you were participating.
Yeah, you said I could listen in.
Looking out at the ocean or lake, whatever it is, when you see a cloud formation, when you hear a Coast Guard alert. And one of the things that I had the opportunity to do in March, April timeframe was I did.
No, it's not.
Delivery.
No, I didn't. I did not.
If we have anybody, Hugh, can you please mute everyone? Make sure everybody's muted. That would be great. Chesapeake. Okay, can you guys hear me again? Okay, sorry about that. This particular picture that I'm sharing with you is an actual picture that I took sitting at the helm with the owner of the boat, Pete. We saw these numbers as we were moving north up the Chesapeake. So my eyes are seeing this information coming across on the chart plotter, which is absolutely horrifying. And we're hearing the Coast Guard give us alerts, and we're basically looking at the sky, and the sky is very tenuous. And what was amazing was that we had a wobble. We had a true wobble with this boat. It was a Leopard 45. And after we went through this part of the, what I'll let Alex speak to a little bit, was maybe a microburst, maybe something else. But what we saw, what we heard, we were concerned, and we were very fortunate that nothing occurred to us. And it was just unbelievable that this is something that we went through. And then lastly, I just want to make sure that everyone knows about sailing and boating with me. So there is a 5-hour on-demand course that is available, as well as the courses that I do live that include rules of the road. I also have sets of flashcards that if you're someone who wants to know the lights, flags, and sounds, that those are something that are available on my site. We do basics of charts and chart plotters. And then I do a number of cruising courses that also include instruction for couples. Very specifically, I will teach you on your boat and help you build skills and helm time. We can discuss how we do that. I also, as I said, just completed 2 weeks of instruction. One was a women's only sailing retreat in Grenada, which was amazing. And 3 women who came back very different than how they got to Grenada with their skill set and their knowledge. And I am also a personal life coach, and I love being able to assist people and living a life they love. And I get to do that every day of my life. So without further ado, I am going to turn over our evening to Alex, and I will get him, we'll get him started. So Alex Avalos, here is your group for the evening. And let's make sure that you are now the host. And
let's see, I should be able to share the screen.
Alex, you good?
Yes, let me see. Without potentially messing up the call, I just want to make sure that I'm pressing the right button to share the screen. Let's see, I have one participant can share at a time. Would you like me to go ahead and stop other screen sharing at this moment?
I've got you as the host.
Okay.
Okay. And I'm going to unmute. I'm going to mute myself. So you're
Okay. All right. There we go. Now we're rolling here. All right. So before I go into more discussion here, I do want to thank Deb. I don't know any other individual who's more dedicated to inspiring others to become sailors and to get into into sailing. So I just want to say that, we thank you for being here tonight and in support of Deb and for learning more about weather and how you can apply that to stay safe while out on the water. So as Deb had said before, I'm an operations manager here at Weather Routing Incorporated. I've been with the company for almost 7.5 years. I graduated from Linden State College, which is in far northern Vermont, with a bachelor's degree in atmospheric science. I work with the team to ensure smooth progress on the floor and operations on a daily basis. I do have local sailing here in upstate New York, where we're based on a lake called Saratoga Lake. So I do have an appreciation and understanding for exactly what entails ideal sailing, what also entails not so ideal sailing or the need to motor. I do have that has also further enhanced my forecasting skills over the course of the last several years. So a little bit more about what our company Weather Routing does. We've been in business for the past 60 plus years. We were founded by a gentleman named Bill Kasich. His first office opened in New York City back in the day. And then over the years, we've slowly moved up the Hudson River to a beautiful little town called Glens Falls now. It's about an hour north of Albany, the state capital of New York. So what else do we do at Weather Routing? Well, we do provide customized forecasts to the specific needs of your yacht. We take safety and comfort as the top priorities, and we look to find the best routes and the best departure days to make sure you're on the most comfortable and the most safe route and departure. We do also provide specialized reports such as climatology studies. And our business is not only limited to forecasting for yachts. We do forecasting for sailing vessels, sport fishers. We also have another division called our commercial division, which specializes in cruise ships, container vessels. We also do forecasting for marinas in both our commercial and our yacht division. We do forecasting for races and regattas and other various rallies as well. So to start, as Deb had said, we're breaking this discussion tonight into two components. The first one is going to be more so a basics discussion, which for those who have attended webinars in the past, some of this information will look familiar to you. And then the second part will be more of an applications and how you can look at cloud structures and surface analyses and how you can link the two, as well as using the forecast to stay safe on the water. So some of the topics in this first part of the discussion we're going to go over tonight include what is weather, as well as what climate is. Now we're going to go into a nuts and bolts discussion about surface analyses and how to interpret various observations that may be available to you, whether that's through the National Data and Buoy Center or through other ship reports. We'll give you the lowdown on exactly what that entails. We'll also go over radar and satellite data, so how you can use that to your knowledge to review and understand what kind of weather is approaching your area, And we'll also go over a topic called ocean currents, which are a very important component to a successful sail, especially for sailing vessels. So, what is weather and what drives it? Well, I can point to that one orange fiery ball in the sky called the sun. So basically what happens is the sun basically drives all weather on planet Earth. And what happens is the Earth emits radiation, or the Earth, excuse me, the sun emits radiation. What comes out of the sun is usually shortwave radiation. So what's happened at that point is the Earth absorbs this radiation, but because the Earth is a sphere, the radiation's distributed unevenly across the surface of the planet. So, as we know, the equator is most directly pointed toward the sun, and it's the hottest part of the world. So, that's a direct result of the equator taking in the most shortwave radiation. Closer to the poles, it's a lot more uneven. And because the Earth rotates on an axis, that's why we have seasons away from the equator. So, the shortwave radiation that affects Earth is less at the poles or poleward and more so equatorward. So what happens is when this shortwave radiation does reach the surface of the Earth, the heat tends to be redistributed. So what'll happen is warm temperatures that you see closer, or the warm temperatures that you see closer to the equator will be distributed poleward. And then for the more indirect areas where there's cooler air because of less direct incoming radiation, that cooler air is directed equatorward. So that gives rise to a phenomenon, no pun intended, called air masses. And so these air masses can vary in terms of temperature, but also moisture. So generally speaking, we're going to use North America as an example here. Across northern North America, closer to the poles, you tend to see Arctic and polar air masses becoming more common. Closer to the equator, they tend to be more tropical. And so these air masses are transporting, their respective air temperatures from their original locations. So from the equator, you're generally going to get these warmer, more moist air masses or tropical air masses. Coming from the poles, they're going to tend to be drier. In coastal areas, you still can get the maritime air masses, which are usually cool, wetter, but they're cool just like the continental air masses, but usually to a milder degree. So you can see here, when you have these air masses moving either northward in the case of the tropical air masses or the southward in the relation of the polar air masses, you're going to have convergence. And what happens is when you have these convergence, you tend to have cold fronts and warm fronts, etc. So these air masses produce our fronts, which are a large and substantial driver to all weather across planet Earth. And the collisions of these air masses produce phenomena such as thunderstorms and other weather systems that exist. So usually what will happen is the stronger a front is or the stronger a system is, you'll see either a larger difference in temperature on either side of our front, or you'll see a stronger pressure gradient in the case of an area of low pressure, which I'll go into a bit more detail on that in a little bit. But usually the tighter the isobars and the larger the difference between the pressures tend to indicate a stronger system. So these fronts are not stationary for the most part. So what happens is that, the fronts are the leading edge or transition out of one air mass into the other. So there's various types of climate classifications as evidenced by the World Map of Köppen-Geiger climate classification. There's 5 subcategories. Of course, closer to the equator, they're going to be hotter and even more moist, except for desert areas such as Central Africa and even up towards the Saharan Desert, which is a little bit away from the equator. But generally speaking, air masses closer to the equator tend to be the most moist. Working your way north, they become a bit drier in the northern hemisphere, and the same holds true in the southern hemisphere, but working in the opposite direction. So the further south you get in the southern hemisphere, the drier and cooler the air masses tend to become. So the 5 main characterizations include the equatorial, which is denoted by class A. B tends to be arid, so for areas like the Saharan Desert, or even Phoenix, Arizona, for example, you tend to find that kind of tropical classification. Warm, a warm classification will include places like Florida, for instance, or even southeastern Brazil. Now, when you're talking about snow, you're tending to get to more northern latitudes in the northern hemisphere, such as New England and New York, where I am, or with southward extent in the southern hemisphere, and then polar. Obviously, that's for the more Arctic locations like Antarctica, far northern Canada and Russia, as well as Greenland and Iceland. So basically, weather tends to focus on things that are ongoing in the shorter term. We could be talking about a week out or even 2 weeks out. We're talking about what's going to happen in the short term, comparatively speaking. Climate tends to focus on the very long term, over hundreds of years, and climate itself is basically an average of weather conditions. So, for example, in the equator area, the weather pattern is pretty persistent there. There's really no variation in temperature there over the course of a year. So, there's really going to be an average of very similar conditions there, but there tends to be more variability further away from the equator in either direction. So now that we've talked a little bit about what climate and weather are, we're going to go over our nuts and bolts discussion about surface charts. So basically on a surface chart, it can indicate numerous weather features. The most common ones you're going to find are areas of high and low pressure, as well as cold and warm fronts, any tropical systems that might be ongoing at a given time. I'm sure everyone knows there's now Hurricane Ernesto, or there's going to be Hurricane Ernesto in the Western Atlantic moving towards Bermuda in the days ahead. There's also troughs that are indicated on surface analyses, and these tend to be areas of low pressure. So one of the things that is important with the surface analyses is you tend to be able to have the ability to construct your own weather briefing for independent planning if you have a good understanding of what each of these features is. So this is an example of a surface analysis focusing on primarily North America and some of the Caribbean islands. As you can see in this shot, it's basically a pretty active and busy map. We have a pronounced gale in the Hudson Bay with a pronounced cold front moving across Ontario and into the northern high plains, whereas a warm front extends from Quebec and even basically to northern upstate New York. Whenever you see the two fronts mixed together with the blue triangles and the red semicircles, that tends to indicate a stationary front, a front that's not moving. These brown dotted lines indicate troughs of low pressure. And I will discuss in a little more detail a bit later in this talk about the differences between cold fronts and troughs in particular. But they do have some similarities too. A purple front that you see on this map is also an occluded front, which basically indicates the overriding of a cold front on top of a warm front that may be slower. And then the H's, pretty self-explanatory for an area of high pressure, and then the L's for an area of low pressure. And you can see here that we have the isobars here, which indicate as the pressures decrease from the center of the high, that's likely emanating out from a ridge, whereas the pressure is increasing outward from the low, that indicates that it's an area of low pressure, basically, to sum it all up. So about high pressure, it's kind of, depending on how you look at it, a high pressure can be a blessing or a problem. And what I mean by that is a blessing because the weather tends to be benign, not really going to have much in the way of any significant weather that could really cause serious concerns if you're out on the water. But obviously the biggest downside is, when you're a sailing vessel, you want to have the wind to motor, and sometimes the high pressure is not going to provide that, at least near the center. So basically areas of high pressure tend to be more permanent, semi-permanent. They tend to move, using the Atlantic as an example, the high tends to move northward in the summer months, and in the winter months, as the seasons cool, it tends to migrate southward. So basically a high center, it's calm towards the center of the high. The higher winds tend to be outward from the high center, which is also known as the ridge. So in the northern hemisphere, highs tend to rotate clockwise. In the southern hemisphere, they rotate counterclockwise. The scientific speak for that in the northern hemisphere is when you have a counterclockwise flow, you're going to have, cyclonic flow. When it's clockwise, it'll be anticyclonic. So high pressures tend to rotate clockwise in the northern hemisphere and counterclockwise in the southern. And usually what'll happen when you have a large area of high pressure is that there won't be really much in the way of cloud cover because of the fact that there's really no lift that's ongoing there. If anything, there's sinking motion ongoing within the high, and that's very detrimental to any cloud formations. So in this example, a large, broad area of high pressure is dominating across the northeastern United States. Not really much wind to work with, so yes, the weather's favorable, but certainly wouldn't be the best news for someone who's looking to go sail in the Gulf of Maine or Long Island Sound, for instance. But as you get outward from the high, you can see that the isobars do increase and they're more compact. So when they're more compact, they tend to result in higher winds. And remember what I said about the clockwise flow around the center of a high. Certainly here, the winds across southeastern Ontario are going to be more southwesterly to southerly in this case because of the cyclonic nature of the high. Now, converse to areas of high pressure are areas of low pressure. So with a high pressure, of course, like I said, weather is calmest near the center of the high. The same is not true for areas of low pressure. And in fact, near the center of low, it tends to be quite stormy and unsettled, with improving conditions away from the low. Now, you have to consider the fact that a front may extend from the low. So, it depends on where you are in advance of the low that the weather might at least be drier. But certainly you can get strong gusty winds, even in association with lows and outward from the center of lows. But the isobars tend to be more tightly packed. And as I said, it's usually pretty unsettled near the center of a low. And whenever you look at a surface analysis and you see multiple isobars compacted towards the center of the low, it's likely to be a stronger system. So, be prepared for, unsettled weather closer to the center of an area of low pressure. And here's an example of an area of low pressure across the lower Mississippi River Valley. What we have here is a cold front extending from northern Mississippi down to the northwestern Gulf Coast, and then a stationary front extending eastward across the interior southeastern U.S. to the Carolinas. And you get this little region in between the two that's called a warm sector. So the warm sector basically entails the most unsettled region because there's abundant moisture and instability that can really fuel thunderstorms. And in this case, you're going to get tropical moisture emanating northward from the Gulf of Mexico. So that only further enhances the cause for thunderstorm development. So a bit more of a discussion on cold fronts. As I said before, fronts are basically the transition boundary from one air mass to the next. So cold fronts usually indicate that, colder air is going to be overtaking warmer air. And usually this colder air is drier, whereas the warm air ahead of it tends to be more moist and humid. So what happens is when you get these cold fronts moving in their respective directions, you're going to tend to see that thunderstorms tend to bubble up, and they can bubble up pretty fast. And when that happens, you get showery and squally weather developing, sometimes very fast. You can see, if you're out on the water, you can see cumulonimbus clouds developing the distance because they can get quite tall. And they can get quite tall that even over open land areas, you can even see them from a distance. And just to kind of add a side story to that, I remember back in the day when I lived in Wichita, Kansas, you could even see cumulonimbus clouds developing over eastern Colorado. Yes, that's how tall they get. And in Wichita, several hours east of the Colorado border. So cumulonimbus clouds are definitely, a sign of something to be reckoned with, and it's worth taking their development seriously. So with cold front passages, winds tend to start out more southerly, and they'll either view or another term that's used in place of veering is clocking, south to west and northwest with the approach and passage of a cold front. And usually the winds ahead of the front will be a bit on the gustier side. And this is especially true if a front is overtaking an area of stronger ridging to the east. That will only further enhance the winds. And the blue triangles tend to indicate the direction that the front is moving. So this front is moving southeastward, and it's emanating out of the northwest. So for this map, you can see it's pretty self-explanatory. There's a cold front emanating from a low over the tri-state region. For those who don't know, that's Connecticut, New York, and New Jersey. And that extends southwestward into the Delmarva, as well as into the interior southeastern United States. And this front is generally moving southward to southeastward, as indicated by the blue triangles. Now with warm fronts, while these have the same purpose that cold fronts do, or they serve the same function, I should say, there are notable differences apart from the fact that a warm front indicates that warmer air is overtaking cold. The weather tends to be less volatile with warm front passages. In fact, usually what'll happen is, there will be steady rainfall, high overcast in place with warm fronts that are lifting northward. And unlike a cold front, which is seeing a colder, drier air mass overspreading a warm, moist air mass, you're kind of having the opposite take place here. So cooler air masses tend to be replaced by warmer, moist air masses. And usually in the wake of a warm front passage, you'll notice an increase in humidity. And winds will tend to veer or clock more from the northeast to the east and ultimately the southeast with their passage over a given region. High winds tend to be less of a common occurrence with warm front passages. They can still happen, but certainly not to the extent of their cold front counterparts. And the red semicircles indicate the northwestward direction in this example.
Alex, this
Yes.
is Deb. Could you go back and speak to the wind veering in both the cold front and the warm front? Jim Brewer was asking that question, and instead of having you keep going, I'd like you to address it if you would, please.
Yes, let me that here. Yes. So what happens is, thank you, Jim, first for the question. So what happens when the wind veers? Let me go back to a map that I have here as an example. So basically, if you think of this large area of low pressure. So what's happening is, as I said in the an earlier discussion, is that lows rotate in a counterclockwise direction. So think of it like this. What happens is, in advance of a cold front that's extending here, and you can tell where the front is located by the kinks in these isobars, the winds will here tend to be more southwest to west in advance of it. But if you notice behind the front, it's generally more northwesterly. So what's happening is, when you look at a surface map, for example, as that front shifts, in whichever direction it's going, the winds behind the front are going to, basically, shift from a south to southwesterly direction to a northwesterly direction, as indicated by the isobars. But another reason why they're called cold fronts is because that northwesterly wind is ushering in a cooler, drier air. Does that make sense? Perfect. Awesome. Thank you again for the question. That was a very great question.
Alex, I'm sorry. I
Yes.
couldn't get to quick enough. So one of the things when we're on the water
Mhm.
that we actually can feel whether it's a warm front or a cold front,
Mhm.
ahead or behind, right? So we know because we experience that as the front is coming to us.
Right.
And as we're on the water, so you're going to have an expansive amount of wind, and that wind is coming ahead of the front, and that front there are choices that we as sailors need to make as to what we're going to do as this front is approaching us. Does that also help?
Yeah, no, absolutely. That does help. I think, certainly, and you can let me know if I'm off the mark here with answering your question. But yeah, no, you certainly with a cold front, moving eastward, for example, the winds increasing ahead of it, especially during the hotter times of year, it's a pretty sure bet that there's going to be volatile weather, usually in the form of thunderstorms overspreading a region. So that's why I would encourage, if you have the access to radar or, Coast Guard alerts, definitely keep those handy. If you happen to be near shore, definitely consider pulling in and waiting for the inclement weather to pass. Certainly Mother Nature fortunately does give us some very good clues that there could be trouble brewing on the horizon. And certainly one of the clues that Mother Nature gives us is, when you see not only the southerly winds increasing, for example, but if you see to your west cumulonimbus clouds bubbling up, that's a pretty sure telltale sign that definitely heed an eye to the sky, and take action as necessary to either get off the water, or if it certainly you can get southerly winds in advance of a front, but the thunderstorm threat might not be as readily imminent. So it's all about judging what's ongoing, usually to your west or your southwest, that would ultimately dictate whether you need to get off the water or not. Because if there's no clouds to the southwest or west, certainly there's certainly some time to buy before that becomes an issue.
Perfect. Thank you, Alex.
Of course, my pleasure. All right. So back on the the discussion about warm fronts. These lift north. In this case, this front is lifting northwestward, as indicated by the red semicircles. So here's an example of a warm front on this surface map, lifting from the lower Great Lakes up through the central and northern Appalachians, eventually overspreading parts of New England and New York. And here's an example again. Here's a warm sector, the area between the cold front and the warm front, as evidence across southern Michigan, northern Indiana, and northern Ohio. So stationary fronts basically behave exactly as their name implies. There's really no movement with them. They're very stationary. However, when you have the convergence of the two fronts, a cold front and a warm front, you usually will get, a focus for precipitation or rain because of that vertical motion that results from the convergence of the two. And then usually that rain does not tend to be strong to severe. It can be heavy at times, but you're not usually going to see strong to severe thunderstorm development with them. So in this example, there's a stationary front across Kansas in eastern Colorado with little movement of the front, and you'd have to look further east to see, of this frontal passage moving closer to the coast. So occluded fronts basically, it basically involves the convergence of a cold front and a warm front. What happens when you have cold fronts overtaking warm fronts is it pushes the warmer air aloft. And think of it this way too, because warm air rises, cold air sinks. So what happens is you mix in the dense, cooler air with the less dense warm air that's also more moist. It forces the warm air upward and the cold air downward. Basically what happens is there's the difference between the two at the end is really not that significant in that, it's a colder air mass moving into a less cold air mass. Let's put it that way. And then basically what happens is because the warm front is slower to move than the cold front, they usually move in the same direction at that point. So as indicated by the triangles, which is typically indicative of a cold front, and the semicircles, which are indicative of a warm front, this occluded front is moving in the northward direction. And in this example, a warm front is shifting off of an occluded front is shifting off of the southeastern New England coast, with the warm front generally extending outward to the south of the occluded front and southeastward towards Bermuda, whereas the cold front itself extends towards northern Florida. So circling back around to troughs, I had mentioned before that there are some similarities and differences between troughs and cold fronts. Basically, the biggest similarity between troughs and fronts are wind shifts. So usually, apply the same thought process with cold fronts to troughs, and you'll get the same result with, the wind shifts here. And the biggest difference is that these usually form on the backside of lows. And you can get unsettled weather, but it's not that common that you get strong to severe thunderstorms with troughs like you would with the main front. And usually it does not result in much of a temperature change. But like I said, you can get showers, maybe a thunderstorm or two. But in comparison to their cold front counterparts, the weather tends to not be severe. You can get heavy downpours with them, but severe weather is usually quite minimal. And they tend to extend outward from the low themselves. So in this example here, you can see the trough is extending, behind the front. In this example, it's worth noting that a trough can develop on either side of a front, but in this example, we're using for this one behind the front. And then you can see further north across Quebec and Ontario, there is a trough actually in advance of that cold front. But the biggest thing to take away from troughs versus fronts is that they only indicate wind shift. A front indicates a wind shift and a temperature change. So moving on from surface analyses to upper level charts, basically the upper level chart gives you an idea of, what the pattern looks like that is conducive for the development of lows and fronts, even areas of high pressure too. So when you see a large digging trough of low pressure in the upper levels, that can be indicative of a very favorable setup for lows and fronts to shift off of the coast in this example. And then further west, you've got a dominating ridge extending across the western US. Excuse me. So with the trough, you will tend to see unsettled weather, as has been the theme of the discussion for related matters with surface analyses. But this large blocking ridge across the west coast usually indicates benign and favorable weather. So reading more into wind barbs, this is certainly an area that understandably can be quite confusing to some because we're accustomed to seeing wind vectors. And usually with the rule of thumb with wind vectors is that, they measure the direction the wind is blowing towards, not necessarily the direction they're coming from. The wind barb aims to achieve the opposite. So basically, whenever you see a wind barb pointing in a particular direction, that's basically indicating which direction the wind is coming from. So in these three examples, you can see in the Northern Hemisphere, a full barb tends to equal 10 knots. A half a barb tends to equal 5 knots. So when you add the two together, 10 plus 5 is 15 knots. Most of our measurements in weather speak are done in knots, but if you wanted to convert it to miles per hour, it would be 17 miles per hour. Now, when you have a single flag, that's indicative of a 50-knot wind. And in this case, because the barb is pointing down, or in this case, to the south, that means the wind's coming from the south. So that works out to a 50-knot wind or 58 mile per hour wind. In this example, the barb is pointing to the southeast at 75 knots, indicated by the flag, which is 50 knots. Then you take 10 knots a piece for the full barbs, 60, 70, and then the half barb is 5 knots, makes 75 knots. And you usually will see these and not the wind vectors on surface analyses. Like I said, surface analyses vectors indicate the direction the wind is blowing towards, but the barb indicates the direction it's coming from. So the Beaufort scale was a table or a measurement system that was implemented back in the 1800s in the absence of the technology that has since developed in the decades and centuries since. But basically, the Beaufort scale is meant to show a comparison or a correlation, rather, between the wind speed and the actual sea state height. So when you think about it, whenever you get a wind-driven sea, that's going to be the result of stronger winds in place. And ultimately, the magnitude of those seas is dependent on the speed of the wind too. And also your location, whether you're well offshore, certainly the seas are going to be more influenced by the winds than, say, immediately along the coast when there's an offshore wind, because the fetch is going to be more reduced. So an offshore wind and along the coast usually is not going to result in a significant sea state, even if the wind is blowing quite substantially along the immediate coast. Whereas if you're out in open waters, say in the central Atlantic, the influence is going to be much more pronounced. And the forces range from 0, which is really nothing to be concerned about. It's flat calm, to force 12, which is basically a hurricane, and 14-meter waves at least. Visibility tends to be very poor in that case. And then, of course, the air tends to be filled with foam just based on the wind and the seas being quite volatile.
Alex, can I join in for a second?
Absolutely.
Yeah, one of the things that I will tell you is I use the Beaufort scale all of the time, especially in my teaching coming out of Grenada, where we have a lot of the catabolic winds that are coming through the mountains, where we have very high volcanic mountain ranges, very different than sailing in the Bahamas than the United States.
Mhm.
However, what I want to point out is that we do use the Beaufort scale because you can look down range as you're sailing, and you can see what you're looking for wind gusts. If you happen to be a racer, any of you guys, women who are racers, you're looking for the puffs of wind so that you can take an advantage of that. For those of us who are cruising, we want to stay very alert and aware, especially when we're around these islands in the Caribbean that are very high, that have the catabolic winds that are moving through them, because it's very easily to have a knockdown occur if you're not paying attention and you're under full sail. A lot of times people don't recognize that that can happen, but when you go from the United States and the Bahamas to a place like the Dominican Republic, where you have 3 very high mountain ranges of over 10,000 feet, same in Puerto Rico, you've got some very different kinds of weather that you have to be looking for as you're sailing and how you're sailing. So the Beaufort scale is something that I would have handy. I would memorize it, and exactly. Especially when I'm instructing, we're looking at what are we seeing ahead of us? What does that tell me? What do I want to adjust with my sails? So this is very important to us, and this is not to be taken lightly. So just an FYI, use it.
Absolutely. No, thank you, Deb, for discussing that further. It's certainly one could say that it was developed a couple centuries ago, but the reality is that even in my line of work, I do still work with clientele who refer to the Beaufort scale as well. So it's definitely, disregarding the fact that it's a relatively older method, it's still a very effective and important tool to use. And Deb, thank you so much for discussing that further.
Sure.
All right. So using a barometer, of course, obviously when you have good weather, the pressure is either going to be steady or it's going to be rising. And conversely, when the weather is deteriorating, it's going to be dropping. So when you're out on the water, you want to take a look at how quickly the pressure is changing. Of course, if it's not changing at all or even rising, really not much to worry about. If it's dropping, however, it's important to be prepared for these changes in the weather conditions, and sometimes you have to be prepared for it quite suddenly, especially if the pressure is dropping significantly, such as 4 to 5 millibars in a 6-hour period. If it's a situation where the pressure is falling 1 to 2 millibars in 3 hours, yes, it's enough to it's noteworthy and worth paying attention to and heeding the caution that is necessary. But certainly, whenever it's dropping at a faster rate than that, that's certainly a cause for concern. And you would generally want to follow the rules, the 1, 2, 3 rule or the 4, 5, 6 rule. And certainly, weather can't be perfect all the time, unfortunately. So it's worthwhile keeping an eye on the drop in pressure and seeing how quickly it's dropping over what period of time. And certainly a smaller period of time is going to be more problematic. So taking a look at surface observations, as I had mentioned at the beginning, there is a very good and thorough database of buoy reports for the United States, at least on the National Data and Buoy Center. There are, buoys worldwide that are quality controlled. You can see the location of these buoys on the map. As you can see in this example, there's a buoy that's being highlighted off of Long Island. So you can see the geographic area, but they also do indicate the coordinate location as well. So it gets you right down to the point where they are. They also show the time that the observation was recorded, and they will tell you what the winds are, the sustained winds, as well as the gusts. They'll even tell you the significant wave height and the dominant wave period. And, certainly what the wave period has generally been over the period of time, also known as the average wave period. It'll also tell the wave direction and the pressure, as well as the temperature too. So there's definitely a wealth of invaluable information. And the best news is that they're quality controlled. So any erroneous data that ends up surfacing on one of these buoy reports tends to be quality controlled and removed. So in this example, here, you could look at a chart at a given buoy over a 24-hour period, more or less, and you can use that to evaluate trends. And sometimes when it comes down to weather forecasting, it's all about evaluating trends. So if you were to, brief yourself on the weather, and you were to look at this chart, there are some very noteworthy things here that can clue you in on exactly, what you might be looking at in terms of the weather over the next, 24 hours or so. So a couple of things to keep an eye on here are the change in pressure. So you can see here, it's basically a wash, if you will. There's not really much fluctuation in the pressure over this 24-hour period. Because of that, you can pretty much conclude that the weather has not changed much in the 24-hour window that's being evaluated. What are some other data points that back that up? Well, if you take a look at the wind speed and the wind direction, it's by and large out of the southwest to south-southwest. So there will be some variation, and that's just part of the nature of the beast, if you will. The winds are generally out of the south-southwest to west-southwest, but the wind speeds and the wind gusts generally more or less do remain consistent, through the duration of this period. And certainly taking a look at the pressure, that's a good first step to determine exactly, how the weather, what the trend has been with the weather in the past 24 hours. You could pretty safely assume, just based on reading this table here, that there's a large area of high pressure in place. And for any fluctuations of the wind, it's likely that because of the clockwise flow of an area of high pressure, this buoy is likely located in the western region of a large high, if not in the ridge along that side, because of the southwesterly flow in place. Ship observations are another great resource for determining, what the conditions are shaping up to be at a given location over a period of time. But a word of caution with ship observations is that these are not quality checked by the ship, and there can certainly be some discrepancies as well. For example, if a ship puts an ASOS at the top of the ship mast, naturally the winds are going to be higher there than they are more at base level. So it's always worth taking these with a grain of salt. If you're taking them at face value on their own, it's always a good idea to look at surface analyses, as well as other buoy reports in the given area to see if there's any consensus or a similarity. Now, if you see a glaring difference between buoy reports and what you see on a ship observation, that ship observation is likely a big red flag. But they do relay a lot of good information at the same time. Similar to buoy reports, they relay winds, they'll relay the waves, and depending on the data point, they will relay the direction on the waves, as well as the dominant period, and they'll even tell you, what the pressure and visibilities are. Now, another thing too is you can't exactly access the 24-hour observation reports either. So that's another negating factor, or an additional con to ship observations versus buoy observations. So another method of determining how what the winds are in a given location, there's an advanced scatterometer pass, which basically looks at the wind-driven sea state to determine what the wind speeds are. And this is a satellite pass that's done about twice per day. Sometimes it may even be less than that, unfortunately. But it can give you a wider swath of what the conditions are in a given stretch. And in this case, you can see off of Newfoundland and out westward. There's basically a good amount of data here that shows sustained 15 to 20 knot winds, and even 20 to 25, with some locally higher up to 25 to 30. But of course, a very limiting factor that's notable with advanced scatterometer, because it's only a once or twice a day satellite pass, is that you will have empty data in between the passes. So it's another data point that can help you to understand trends with the forecast, but do note that, of course, that by design, there will be data missing. So moving on to radar itself. Now, this is certainly something that, if you can, while out at sea, take with you. I strongly would recommend that you have access to the radar. And of course, I know there's technology like Starlink out there that's certainly allowing more sailors to take internet and phone connections out to sea. For others, that's not so much the case. So internet connection might actually be limited, as well as cell signal. But in the meantime, radar is a very good measurement of precipitation that may be ongoing over a particular area. It also is very good at measuring the intensity of said precipitation. So whenever you see hotter colors on a radar, that's more likely to indicate intense precipitation that's ongoing in a given area. So here you can see, there are several areas of warm colors offshore southeastern Texas and southwestern Louisiana, which are very good indicators of thunderstorm development. And these cooler, greener areas are likely just showers or maybe some heavy downpours on their own. With respect to radar coverage across the United States and all U.S. territories, there are 160 sites. They cover a 290 nautical mile range. And so what happens is you'll usually see overlap between radars to make sure there are no gaps, so that, in the event of severe weather, the last thing we would want to have is a radar that's not reaching a certain area. So there's always that overlap. Sometimes radar beams are complicated by, mountainous terrain. And that's an unavoidable situation, unfortunately. So it's good to have other radars nearby that can pick up on areas that are otherwise affected by the closest radar. But no coverage goes beyond those 290 nautical miles. One of the other things too is that while we have good coverage of radar here in the United States and U.S. territories, coverage tends to be more spotty worldwide. Across Europe, there's some good radar availability, but other parts of the world, that's not so much the case. Radars are also very useful in determining the potential for waterspouts and tornadoes, which are certainly an important and understandable concern for sailors who might be out on the water. So you can note on a radar what, the type of storm that might produce a waterspout or a tornado, and these are known as supercells. They're best defined by their comma that you note on the southern side of a system. Usually what happens with the waterspouts and tornadoes is you will find them in this comma-like hook feature on the south side of a supercell. Up here, it's not so much of a concern, but definitely where you see this hook, that's the area you need to be most pay most attention to. If you have access to radar and you're out on the water and are concerned about the potential for water spouts. Fortunately, out on the water, there's, the more limitless horizon versus being on land, and you can see longer distances at any weather that's approaching or happens to be off in the distance. But having, the ability to see it on radar is another resource that, helps to keep you safe and informed. So, digging a little deeper into radar, you can spot tornadoes and water spouts on velocity fields, and you can note the rotation. In this case, we've got the warmer colors basically pointing in the direction of the radar or moving in the direction of the radar, whereas the colder colors are moving away from it. That creates that flow, which indicates the rotation of the tornado or the water spout. So moving on to satellite imagery. Satellite imagery is very useful to determine sky conditions. Basically there are several different types of satellite imagery, such as visible and infrared, as well as water vapor. There's pros and cons to each. I'm going to go over those in a bit more detail here soon. Basically satellite imagery can be used to determine areas of fog as well as thunderstorms, and weather features such as outflow boundaries, which are certainly something that, can be experienced out on the water. And these do not have to be in the vicinity of a parent thunderstorm for you to experience them, but they do emanate out from parent thunderstorms. And basically, outflow boundaries can be called mini gust fronts because they're associated with gusty winds. So visible satellite imagery is perhaps the best resolution satellite imagery. This imagery is particularly defined by its availability during daylight hours only. So that happens to be, its biggest liability. With the higher degree of, resolution, you can see various types of clouds, including fog banks. You can also see thunderstorms with cumulonimbus clouds. And you can see thunderstorm structures as well with those. But there are some good resources such as NOAA, as well as, from my personal experience, College of DuPage, which is based in Illinois. There's also the GHCC website. These are all good resources that you can use to find not only satellite data, but radar data as well. Here's an example of satellite imagery across the Leeward Islands and the Lesser Antilles. You can see because the clouds look whiter and puffier, it's more likely to be thunderstorm development. But going back to that topic about the gust fronts, if you look here at these ribbon-like features, that's indicative of gust front activity. So these fronts are likely emanating from these thunderstorms to the north, or these thunderstorms to the south. And then further north across the southern Leeward Islands, you can see a thin ribbon of gust front material ongoing in those areas. So a thunderstorm doesn't necessarily need to be overhead for you to experience the gusty winds. These develop and originate from the parent thunderstorm, and then they move in their respective directions. So the weather overhead can actually be quite nice when you get these gusty winds. So you can see thunderstorm development as well, as indicated by the puffier features that you see across southeastern Texas and southern Louisiana. Where there's thinner clouds, usually they'll be darker on satellite imagery. So usually when you have thinner clouds, it's more likely to be something like cumulus or even higher cloud cover. These thinner clouds are more likely to be cirrus. Or even patchy cumulus clouds. But the whiter and puffier versions of the clouds that you see here tend to be indicative of thunderstorms ongoing in a particular region. Now, for those of you who sail and have sailed in New England or who come up to New England, even to vacation or what have you, fog is a very common thing here in the summer. And basically the reason for that is because of the notable temperature differences between the mainland and also, more open waters like the Gulf of Maine, for example. So it tends to be more prolific in the Gulf of Maine, for instance, because the sea surface temperatures are cooler. than it would across Cape Cod or even Southern Rhode Island or Long Island. But needless to say, it's still more common in coastal areas across all of New England during the summer months because you get that larger temperature gradient between land masses and water masses. But on visible satellite imagery, you can see fog banks. It tends to be smoother than what you see with thunderstorms on visible satellite imagery. And you can see they tend to be darker and smoother. And if you loop visible satellite imagery, you can see the motion of these fog banks. Switching gears a little bit from visible satellite imagery to infrared satellite imagery, cloud temperatures tend to be the name of the game with this kind of imagery here. The biggest pro for infrared imagery versus visible satellite imagery is, of course, the fact that you can use it anytime, day or night. However, the trade-off is the resolution of infrared satellite imagery is considerably lower than that of visible imagery. So it's harder to see finer scale features like gust fronts and fog banks. But basically think of it this way. Temperature decreases with height up through the troposphere. And then basically what that means is by cloud temperatures, with height, the temperature is cooling. And whenever you see taller cloud tops, that indicates that temperatures are likely to be colder up that way. So infrared satellite imagery is a very good tool to determine, cloud heights and cloud tops. And certainly you can refer to the color key at the bottom of any infrared satellite imagery to get an idea. But in this instance, you can see here, the warmer colors indicate taller cloud tops, or in this case, colder cloud tops, which is likely to indicate thunderstorm development because they just happen to be the tallest. So there's a few areas of notable thunderstorm development here, most pronounced across the Yucatan, as well as south of the Rio Grande. But other activity includes across Jamaica and the Cayman Islands, as well as Cuba. So one of the last topics of discussion that we will be talking about here in the basics, nuts and bolts section of our webinar tonight are currents. This discussion has been a lot about weather, but currents are also very important for sailing too. And certainly there are larger and smaller scale currents. I think one of the most prolific currents that we have here in the United States and in the Western Hemisphere is the Gulf Stream. That originates in the Gulf of Mexico and ultimately ribbons around southern Florida before, working its way up to the Carolinas and ultimately out to sea there in the more open waters of the Western Atlantic. So smaller currents can be affected by the tides and the phase of the moon, which is a pure driver of tides. But certainly larger currents like the Gulf Stream are going to be less amenable to change, even in the face of the tides. Or if there's a significant weather event, it's unlikely that the Gulf Stream is going to really change much. But you can have high variability in the Gulf Stream over a short period of distance, or any other currents for that matter. Excuse me. So here you can see the Gulf Stream that is working its way up the Carolina coast. And then ultimately ribboning out into the Western Atlantic. You can see here there's a few phenomena here, these rotating gyres called eddies. Basically, an eddy that's rotating clockwise is going to be a warm water eddy. And basically what happens here is warm water is replacing colder water. Whereas with a cold water eddy, they rotate counterclockwise, and cooler water tends to replace warmer water. Now, the next image I'm going to show you is an example of the sea surface temperatures. And it's actually quite interesting to look at when you consider the Gulf Stream and the gradient of the temperatures across the Western Atlantic. So you can see the ribbon of the Gulf Stream temperatures, or the Gulf Stream seas, coming up and the warmer temperatures that are associated with them emanating out into open waters of the Atlantic. But north of the Gulf Stream, you can see that the temperature does drop off pretty significantly into the Gulf of Maine and in New England. But that's very common. Sea surface temperatures in New England, for example, tend to remain in the 50s and 60s into the summer months. excuse me. But further south, when you get that Gulf Stream emanating eastward, you tend to see those higher temperatures associated with the seas. And with that, that concludes the first part of our discussion.
Great. Thank you, Alex. I have a couple questions for you that I want to bring up real quickly because we are limited and constrained by our time.
Sure,
So,
absolutely.
Janice Wheeler is asking Alex where she feels like the conditions on a 7 square mile lake that she is on are very different than blue water sailing. Obviously, that is a true statement. And she feels like weather forecasts are simply not accurate. So what other background should she be looking for to have to forecast ocean travel?
Well, thank you, Janice, and that's a great question, and I really appreciate it. Certainly, as far as the background to forecast ocean travel, I think even you don't necessarily need to have a professional background to do that. For example, like a lot of the clients that I work with, they when they speak with me or my colleagues, they'll usually take a look at their resources and then consult us for professional advice. But definitely what I would suggest is, have multiple resources and be able to, if you're able to determine what you feel is more accurate with those resources, that can give you a better idea as to what kind of forecast you're going to be looking at. But there certainly doesn't need to be a professional background to be able to monitor the weather. But I would definitely suggest having a resource that you would be comfortable with.
Great. Thanks, Alex. One of the other things that I'll say about being an ocean sailor is that as you're sailing with other people and you're either moored or in a marina, people have discussions about weather all the time. So people are looking at the weather and what they're seeing from their
Right.
Starlink. They're downloading from as many resources that they have, and they have various resources that they prefer. So the more that you're out there, the more that you're talking to others, you're looking at other people's expertise, again, using people like weather routing as a resource for you. So you do have questions, you feel like I want that expertise, you've got that available to you. Last question I had from Stephen, and Stephen was asking about the different models that depending on the regions, when we're looking at weather forecasting, hurricanes, and these different models that we see, like Mr. Weatherman doing all the 7 different models of where the hurricane's going to go. What is the difference basically of these models and what is the value of them?
I'm so sorry, Deb. Would you mind repeating that question?
I'll try.
Okay.
The question really is the kinds of models that we have when we have someone who's forecasting the hurricanes and we see these spaghetti strands.
Yep.
The GFS, the ECM, WF, the UKMO, all of these are different models.
Yep.
And what's the difference of the models and why is it important to us?
So basically, there's an algorithm that governs the models. They run on the premise of the atmosphere, being fundamentally chaotic. And so basically, when the atmosphere is fundamentally chaotic, any slight change in the current weather that's ongoing can have, a domino effect on the weather that happens, say, a week into the future. So these algorithms basically react to these changes, at least long range changes, differently. As we get closer into the shorter term, they tend to come into more agreement, but you can still get the discrepancies with them. But basically, they aim to provide any person with additional knowledge on the forecast in the near term and the longer term.
Okay, perfect. And so just to wrap things up, because we have 3 minutes before we go into our next session. And so, Alex, you guys, every session that we do offer a free weather routing forecast, correct? And so I will be putting out an email tomorrow, guys, with the information of how you can get that from WRI. And I also have a comfortable cruising course that is available to you at no charge on September 20th. So please check your email tomorrow and I will send you your follow-up and you will have your information about how to get your weather forecast with Alex and how to sign up for the next class that again is value add to you. So again, thank you so much for being here.